It's my pleasure to introduce today's speaker, today's scholar, Dr. Sabbir Salek. He is our senior engineer at TraCR. Today he'll talk about quantum computing threats and opportunities. Dr. Salek's dissertation also focused on quantum computing and its relation to cybersecurity. And I'm very proud to say that he was my master's and PhD students. So he has my superstar designation. He's a critical thinker and an awesome researcher and an absolutely best engineer. I'm so glad to have him as my former student, and I call him Dr. Quantum because of his expertise and knowledge in quantum computing, quantum AI. So now I'll request Dr. Salek to let us hear from you about your quantum computing research. Thank you.
Thank you, Dr. Chaudhary. Thank you, Megha. Thank you, sir, for the warm introduction. Good afternoon, everyone. It's my pleasure to be able to join with you today to talk about few of the research projects that I've been working on with TraCR. So as Dr. Chaudhary was mentioning, okay, so let me please share my screen. So, Megha, can you confirm if my screen is visible to everyone?
Yes, yeah, it's perfect.
Okay, thank you, sir. Thank you. So, yeah, so good afternoon again, everyone. I'm Sabbir Salek. I'm a senior engineer of TraCR. I'm also working as a senior engineer for the other UTC that we work with, CR2C2. And today I'm going to talk about mainly about the quantum computing threats and opportunities. And I'm going to present a few projects that I have worked on with TraCR on quantum computing threats and opportunities, primarily focusing on the cybersecurity aspect of transportation systems and infrastructure. Uh, so before we dive into all the technical descriptions of the projects, so I quickly wanted to look at two very significant incidents, cybersecurity incidents that we have been informed by popular news channels in the recent times. So I have included two incidents here. The first one is actually very recent. So it's from the New York Post. They covered the news on March 12th regarding the FBI's warning to iPhone and Android users. Because as you know, at least me, I personally know that I have been receiving a lot of like the fraudulent messages from different unknown entities. I don't know. They're asking for, payments to resolve some outstanding balance or something. So most of those SMS that I'm receiving, I guess a lot of those are from different attackers trying to get like sensitive information, maybe credit card information or social security information from people so that they can later use it for attack purposes. So it's a very recent news. And another news that I wanted to highlight was the Colonial Pipeline because of the impact of the attack. So the first one, it shows like how frequently the attacks are happening, and the Colonial Pipeline, it informs us how impactful a cyber attack can be. So the Colonial Pipeline incident was basically a ransomware incident where a ransomware group called DarkSide, they hacked into the Colonial Pipeline's IT network, and they encrypted some of their like the some of their information into their inside their database, export or exfiltrated some of the information outside the network, and they asked for the ransom. And eventually, the Colonial Pipeline got back hold on their system after paying a considerable amount of money. This news is showing 5 million. Some other resources have shown that they paid around 4.4 million US dollars to get back hold of their system. The good thing about the only good thing about that attack was that the attackers were not able to actually get into the operational technology network of the Colonial Pipeline. They were able to only infiltrate the IT network. So the Colonial Pipeline authorities, they actually shut down their entire system to make sure that the attacks do not propagate from their IT network to the OT network. And if the attackers were able to infiltrate into the OT system, who knows what could have happened, right? We could, like, months of disruption might happen due to that. So this highlights like how important it is these days to consider cybersecurity, and the US Department of Transportation, as you know, they also acknowledges it. So they're saying that no longer we can separate security and safety, and cybersecurity is one of the most talked about topics these days because of these reasons and cyber attacks. Okay, so a quick look at how the cyber threats are escalating for different modes of transportation, starting from roadway transportation to rail, to maritime to aviation. So as we can see that there has been a considerable or significant increment in cyber attacks over the past maybe 5 years. Even if we consider the last 5, 10 years, we have been seeing uh, a major surge in cyber attacks in all modes of transportation. If we look at the maritime transportation, we see that from 2017 to 2021, different resources are saying that there has been a 900% increase of cyber attacks. For aviation, it's over 500% uh, between 2019 and 2020. So just in 1 year, it increased over 500%. In railway, it increased over 200% from 2017 to 2022. For roadway transportation, it increased above 400% from 2017 to 2022, according to many resources. So it shows us how critical it is to take actions or steps to protect the critical infrastructure like transportation systems from cyber attacks that are happening as of now, and also for the cyber attacks that could happen in the near future. So in this webinar, I'm going to actually highlight on three different projects that are focused on three different aspects of connected autonomous vehicle cybersecurity. So the first aspect that I'm going to talk about is how we can secure, I mean, the need for securing the in-vehicle network. So as you know, we have many sensors. The new vehicles or the intelligent vehicles that we see these days, they have many sensors, camera, radar, other type of sensors, GPS, and so on. So all these sensors and their corresponding electronic control units, they all communicate with each other, and they need to communicate with each other on a regular basis to keep the operations running within the autonomous system, right? And for that reason, actually, there is mostly a wired network inside every vehicle that is called the in-vehicle network that connects all these electronic control units, sensors, and other systems so that these nodes can communicate or exchange information among each other to make sure that the autonomous operations are running accurately. So the first thing that we're going to talk about is how we can secure this in-vehicle network, what people have been doing, what type of attacks can happen, and how we can secure these systems with the quantum approach. The second thing we're going to talk about is how we can, so inside the vehicle, we don't only have connectivity, but connected autonomous vehicles have also autonomy side of it, as you know. So the autonomous decision making or the perception or the autonomous control, those aspects must be secured as well for a safe navigation of connected autonomous vehicles. So we are going to talk about how we can use quantum computers for securing the autonomous perception uh, and decision making. And then the last project that I'm going to highlight on, it is focused on the cryptographic requirement of communication in transportation. So, and that can include one connected vehicle communicating with other connected vehicles on the road, or communicating with the roadside infrastructure, or communicating with traffic signal controllers, and so on. So all these communications, these are essentially wireless communication if one of the nodes is mobile, right? So if two nodes are not mobile, if both of them are static, then maybe we can have a wired connection. But otherwise, when communicating with a moving vehicle, it has to be a wireless communication, as you can see. So how we can make that communication more resilient in terms of confidentiality and so on. So we're going to talk about that. Uh, so moving on to the first project. So the first project that I'm presenting, it's about securing the in-vehicle network of a connected vehicle. And we're going to talk about how we can do it from a quantum approach. So how we can use quantum artificial intelligence, in particular, how we can use hybrid classical quantum approach to secure the in-vehicle network of a connected vehicle. Now, the in-vehicle network is actually is it's very open, right? So anyone can actually connect to the in-vehicle network if they can just connect to the onboard diagnostic port that we typically use for checking like the vehicle status, or if we have any warning message, we typically hook up a onboard like diagnostic device to the port and look at the warnings and see like what the warnings are coming from. So that's essentially one of the entry points for attackers. If an attacker wants to access and see like what messages are being communicated within the in-vehicle network, what different electronic control units are saying, what are the status of different sensors or the actuators, an attacker can just hook their device to the onboard diagnostic port and they can look at all these messages. So that means that there's essentially no confidentiality here. All the messages are public if given if someone is able to connect to the in-vehicle network, of course. And there are many ways to do that. They can do it through infotainment system, through OBD port, as I mentioned. They can try to connect wirelessly as well. So, but anyway, so the main issue is then anyone actually can connect to the internal network and they can look through all those messages. So basically there's no confidentiality. And another interesting thing is to make the adoption easier. So the common protocols, so the most common protocol for in-vehicle network is known as the controller area network protocol. It's actually a completely unencrypted and unauthenticated protocol. So it doesn't have any encryption requirement. So all the messages that we see in the internal network of a vehicle, those are not encrypted. Those are hex coded, but not encrypted. And also there's no protocol to authenticate to make sure that the message that I'm looking at, it is actually coming from the node that it says it is coming from. So there's no way to verify that actually the message is coming from that node. And that creates several issues, right? So what happens is that anyone, if an attacker is able to connect to this network, uh, he or she can just randomly inject random CAN messages, and they can essentially flood the network, violating the availability of the system for other like regular nodes or authentic nodes, right? And also another thing an attacker can do is they can simply look at the previous messages from different nodes and they can start replaying those messages into the CAN bus network. So if we develop, say, an intrusion detection system based on our knowledge of how like regular CAN messages look like, that would not be able to detect these messages. If you just take authentic CAN messages and replay them in the network, then all those messages are looking very much similar to authentic CAN messages. So you cannot have a intrusion detection system trained on regular and attack messages be able to identify those authentic messages, right, that are being injected into the network. So that's another issue that we do not only need to look at each messages, but we also have to understand what each message actually imply, and also what each message is. So each message, if you think about a CAN message, what it can contain. So as I said, so basically a message comes from an electronic control unit or a sensor. That means it includes information about the sensors, information about the actuators, right? Now, this information are basically status of different systems within your vehicle. And if you think about, say, for example, a particular system, say, let's talk about the tire pressure monitoring unit. So you have a tire pressure monitoring unit that is constantly monitoring your tire pressures and letting you know whenever it feels that, okay, your tire is maybe running low on pressure, it gives you a warning so that you know that, okay, now I have to inflate my tire. So those kind of information are included in the CAN messages that, okay, say this is right now your tire pressure is maybe 35 psi. In the next timestamp, it is 34 psi, depending on the weight of the car or how the vehicle is operating. It can change from time to time, right? So, but you do not expect to see maybe, okay, one moment you see 35 psi, the next moment you are seeing maybe 15 psi, the following moment you are seeing again 40 psi. So that should not happen. That tells us that all these messages, if we look at them individually, so we understand the status of those associated nodes for a given time period. But if we look at them over time, we can actually understand how the measurements are evolving over time, right? So tire pressure, for example, it can increase or decrease over time, but not probably by magnitude of 10 or 20. So if we look through these messages over time, we might be able to detect that, okay, so this message is claiming that my car's tire pressure is now at 20 psi, but I know that it should not be at 20 psi, it should be 35 psi. So that looking at that, maybe we may be able to develop some intrusion detection system. So we don't need to, so not only we need to look at each messages, but also we need to look at them, how over time the status of different sensors or actuators are propagating. So that would also give us an insight to detect the intrusions. And we are going to see how we can combine these two. So not only just looking at individual messages, but also how those messages are informing about different nodes status propagation over time, and how we can utilize those information in a intrusion detection system framework that incorporates quantum computer, uh, and we can essentially detect the intrusions in the system. So as I mentioned, so the controller area network, it's basically, as you know, it's a broadcast-based system, like a local area network. So anybody connected to the network, they can inject or broadcast any message anytime. It's a completely open broadcast-based message communication system, but it is dedicated channel for in-vehicle controller units. So to be able to inject messages, we actually have to connect to the in-vehicle network. Uh, but there are certain issues with the communications. As I mentioned, the first thing is that it lacks standard security features. And that means like it doesn't have any authentication requirement. It doesn't have any encryption requirement. So all the messages, those are not encrypted. Anybody can read them. Anybody can understand what the current status of the vehicle is. And if an attacker is sending us a message, we have no way of knowing where the message is coming from because there is no authentication. The second thing is the vulnerability associated with the broadcasting system. So typically controller area network, they utilize what's called an arbitration ID based priority broadcasting system. It means that every node in the vehicle or every electronic control unit that is connected to the controller area network has an associated ID. And that ID is assigned based on the priority of the information it is broadcasting. So say, for example, maybe we do not need to know a car's weight every second, but we need to know the actuators, a particular actuator status at every tenth of a second, right? So that particular node will have a higher priority of message broadcasting over other nodes, the nodes that we don't need information on a regular basis from, right? So it has that priority-based messaging system. And if you think about it, so if an attacker, how an attacker could exploit this broadcast priority-based broadcasting system. So the way it works is that so every node has an associated ID, and the smaller the ID is, the higher the priority is. So it means that say a node we are there, say for example that we have two nodes. One node we are assigning ID 001 and another node we are assigning as 002. Since 001 is a lower number, so the first node will have a higher priority of message communication compared to the second node. So that's just an example, very easy example of how it works. And if an attacker thinks about it, so he or she can actually continuously broadcast messages with an arbitration ID 000, right? Because any node will not have a higher priority than 000. That is the lowest number in the arbitration ID system. So if an attacker uses that to continuously inject random messages that has no meaning at all, he or she can essentially flood the network and completely disrupting the system, disrupting the availability of the CAN network. So that's one of the problems. And then another thing is actually not very difficult to actually inject CAN messages into the controller area network of a vehicle. You can inject it through OBD2 port, as I mentioned. You can utilize the infotainment system. You can utilize wireless communication as well. Now, before we look at how we can detect these intrusions or the messages that are coming from different attackers, we first need to understand, or we first need to look at how the actual data frame of a CAN message look like, right? So for this project, what we did is based on each CAN messages, we actually generate an image, and we use the ability of a generative neural network to reproduce image. So we know that generative neural network can reproduce images, right? Or generate images based on what it was trained on. So the approach that we have taken in this particular project is to leverage that ability of generating images. But as you know, CAN messages are not image type uh, data, right? These are more like textual information where you have information about the maybe the cyclic redundancy checksum, or information about the data itself, or how long the data is. So all those information are within the frame of a CAN message. So this diagram actually shows a typical frame of a CAN message. So it starts with a starting bit, which denotes the SOA for the start of frame. And then you have certain bits allocated for the arbitration ID that I mentioned. And then you have certain bits for the control. You have certain bits for the data itself. You have certain bits for the cyclic redundancy check. You have certain bits for acknowledging any previous messages, or receipt of any previous messages. You have a end of frame. So that's how it is formed. So every message should have this. Uh, but the particular fields that we focused on for this particular project are essentially the timestamp, the CAN arbitration ID, the data length code, and the data itself. So the timestamp tells us at what time the data was broadcast, right? The CAN arbitration ID basically tells us where the message is coming from. The data length code tells us how long the actual data is. So it can be 8 bits, it can be up to 64 bits. And the data, which is encoded in hex string, that tells us what the actual data is. Now, as I mentioned, it's not encrypted, but it is still encoded. So just by looking at the data, we cannot make any meaningful information out of it, because it is encoded in hex string. So the first thing we need to do is we need to decode it to understand what the message is talking about. So as I mentioned, yeah, this project is about a hybrid quantum classical intrusion detection framework, and it utilizes the generative ability of generative neural network. So, and we are talking about the image generation, right? And as we showed, the textual data that comes in a CAN network, that's not an image. So what we do is we actually convert these CAN messages into a corresponding CAN image, and then we process it with an image classifier that we have trained on the using the quantum machine. So there are 4 steps in this approach. So in the first step, we will construct the CAN messages. The second step, after constructing the CAN message, we extract meaningful features out of that image. In the third step, we encode it in binary format, and there's a reason to do that. We're going to talk about that in details in the next few slides. The reason is that the generative network that we are utilizing here is actually a restricted Boltzmann machine. The motivation to utilize restricted Boltzmann machine is because it's very lightweight. So as you know, the generative normal, if you look at any other generative adversarial network or any diffusion network, those are basically based on the convolutional approach, and they have a very high requirement of memory. You have many thousands of nodes, and you have to save their weights and biases to be able to use the model for classification, right? In contrast, a restricted Boltzmann machine is just a 2-layer generative neural network. So it has a visible layer and it has a hidden layer. And using just these 2 layers, it is able to generate meaningful information, or images that are very much looking like real images. So that's the motivation for us to use the restricted Boltzmann machine. And the restricted Boltzmann machine is traditionally, it uses like binary values for each of the neurons. And that is why we have done a binary encoding at the third step. And after doing that, we go on to the image reconstruction, where we are using that restricted Boltzmann machine that we have trained. We use that to basically reconstruct the images. And by reconstruction, we get all the labels that tells us whether this image is a regular CAN image or it is a attack CAN image. But we are going to talk about that uh, in details in the next few slides. So if I start from the first step, so as I mentioned, the encoded data, as we can see, it's in hex format, and it's not anything meaningful. So the first thing is we have to decode it. And the way to decode it is actually there are these files called database CAN. Uh, there's these database CAN files are actually specific to what vehicle models we are dealing with or what vehicle brands we are dealing with. So for each type of vehicle, there is a particular database CAN file that we have to use to be able to decode it into meaningful features. So in the first step, we actually utilized those kind of database CAN files, and uh, there's a repository in the GitHub that is known as OpenDBC. It's an open access database CAN repository where you can find most of the most popular vehicles database CAN file. So using those files, first of all, we decoded the encoded data into meaningful features, right? So in this particular example that I'm showing, so you see that the data was hex coded, and after we decoded the data, we got about 13, we got exactly 13 features. And each feature is associated with a particular node, which can be an electronic control unit or a sensor or an actuator. And it talks about the status of that particular node. So all these features, they have an associated value, as you were saying, and those values indicate the status of that particular feature. Uh, Now, one approach could be is that we can just train a neural network model or an artificial intelligence model that can just look at these features and tell me like whether this message is a regular CAN message or a message from an attacker, right? So we can train it on regular CAN messages. But the issue with that is that what if an attacker is copying, or maybe he or she is listening to all the communication in the controller area network, and after gathering enough data, the attacker starts replaying those messages. And it's replaying those messages by broadcasting them back into the CAN network, right? Now, all those messages that the attacker has recorded over time, those are authentic CAN messages coming from authentic nodes inside the vehicle. So if the attacker is replaying those, we have no way of knowing whether this is a real message or a false message, right? Even if we train a neural network on that, it will not be able to detect the false messages because it's the same authentic messages. So what we need to look at is not only that particular message, but also some previous messages from that node to understand, okay, given the previous status, the node should be maybe right now here, not probably very off, right? So to be able to do that, what we do actually, we look at the previous consecutive messages from that particular node. So this node, when we decoded it, we got 13 features. And what we do is we look at exactly the last 13 messages from this particular node. And then by stacking those messages one top of each other, we create a square shaped image. So for example, for this node, we have decoded and got 13 features. To be able to generate a square picture, we need like 13 previous messages then. So we look at the 13 previous messages from that node, and then we construct the 13 by 13 CAD image. So then we have the CAN image that is built on the previous 13, the last 13 messages from that node. And each of the rows of this image, each of the pixels of on each row, it tells us about the features that we have extracted, right? So now we have, on each row, we have one CAN message, and each pixel is telling us about status of different uh, different electronic control units or sensors. And if we go down one layer at a time, the bottom layers of those figures or those images, those are telling us how the image, how the node was, what was the status of the node in the previous timestamps, right? So we accumulated both information then. After doing that, what we do is basically we use a deep neural network to extract more features or more essential features that are essential for image classification. So basically classifying between whether this is an attack image or a normal regular CAN image. So we use the deep neural network to extract those meaningful features. And at the same time, we resize it from whatever the size was before to an 8 by 8. So in total, we then have 64 pixels. And there is a reason we do it like that way. We'll talk about that when we move on to the restricted Boltzmann machine part. But that's how we have constructed each image. So every image will now have 8 by 8. So in total, 64 pixels. After that, we resize the CAN image. So we kind of horizontally compress it from 8 by 8 to 8 by 6. So basically, we reduce two of the columns to be able to. So our motivation is those two columns that now we have reduced. We want to use those two columns and the pixels in those two columns for the label of that image. So label meaning like whether this image is from an attacker or whether this image is uh, from a regular node within the in-vehicle network, right? So after having that resized CAN image, what we do is we, as I mentioned, so we have to use a binary thresholding. The reason is when we are using the lightweight restricted Boltzmann machine, those are typically they deal with binary values for the neurons. So what we did is every pixel, we converted it to a binary value, either 0 or 1, depending on what value it had before. So if it's less than 0.5, it's 0. If it's zero point 0.5 or more, we encoded it as 1. So that gives us an image that is completely binary encoded and of the size 8 by 6. And after doing that, we add, in the last layer, we add the embedding in the last two columns. So basically here, as you can see, the last two columns, all the pixels are denoting 1. That means that this is an attack image. So if it is an attack image, we denote it by 1. If it is a normal regular CAN message, we denote it as 0. So if all these pixels were purple, then we would understand that, okay, this is a regular CAN message. In this case, this one is an attack message. So then we have this figure. In this figure, we not only have the features, we also have consecutive previous scan messages from the same node. And on the rightmost two columns, we have dedicated it for label embedding. So we have the embedded labels here. So all these pixels, they are showing that, okay, this is a CAN message that is coming from an attacker, not a regular or authentic source. All right. And then the last step is basically now that we have the CAN images, we want to train our neural network to tell apart which one is a regular CAN message and which one is a uh, an attacker generated message. And the approach that we take is a restricted Boltzmann machine approach. So a restricted Boltzmann machine is basically a two-layer generative neural network where you have a visible layer and a hidden layer, and the neurons from the alternate layers are connected. And it utilizes an energy-based approach, so it has an energy function. So when we are training the restricted Boltzmann machine, our goal is to drive the energy to the lowest energy state. And if we can drive the energy, the whole energy of the restricted Boltzmann machine, the way we define it, if we are able to drive it to the lowest energy state, then we will have the lowest associated cost. Meaning, like now, in that stage, we are actually able to generate the most realistic CAN images based on what it was trained on. Uh, there are many ways of training restricted Boltzmann machine. The most common and popular way of training restricted Boltzmann machine in classical computer is by using contrastive divergence. So what it does basically, we are going to talk about some probability distribution in the next slide. So what it does is it takes samples from the conditional probability distribution of the model, and then trains the model based on that. So it's not considering all the probability distribution, but only a portion of it by assuming that all the neurons are independent, in which in our case, which is not definitely right, because as you can see in the restricted Boltzmann machine, for the visible layer, we assign 64 neurons to each of the 64 pixels of the image. So each pixel has an associated neuron in the visible layer. And as we mentioned, so in a CAN message, actually the features are not completely independent. They have some dependency. And you can think of it like if the car has a higher weight, your tire pressure will be higher. If the car has a lower weight, your tire pressure will be lower, right? So so the messages that we are getting from different nodes and the features that they are representing, those features have some interrelationships. They are not completely independent from each other. Uh, and that's the problem with contrastive divergence when we are using classical computer to train a restricted Boltzmann machine. If we use contrastive divergence, it assumes that all those neurons, they are acting independently, and it is not able to capture the interrelationship while we are training using contrastive divergence. Uh, in contrast, when we use the quantum computer, we can actually use a quantum annealer, and the approach is known as quadratic unconstrained binary optimization, or QUBO, it is called. So we can actually utilize this QUBO approach to train the restricted Boltzmann machine. And the benefit is, unlike the classical computer, the QUBO actually draws samples from the original probability distribution, not considering that each layer or each node are independent. So it is able to capture the interdependency between these different features that we are dealing with. Uh, a quick look at the energy function of a restricted Boltzmann machine. It's a simple energy function that basically accumulates, so each neuron multiplied by its associated bias. And also for the interaction between neurons, we have the interaction term, which is a quadratic term. And then from that energy function, we can actually calculate the probability of a given state. So a particular state of the visible and the hidden layer neurons. We can actually compute the probability. But to be able to compute the probability of one particular state, we have to know all the different combinations, all the different possible combinations of the hidden and visible layer neurons. But that is extremely hard to compute, as you can think of, because there are 64 neurons on each of these layers, and each neuron can take two values, either 0 or 1, meaning like there are many different possible combinations out of these 64 and 64 128 neurons. And when we're using the classical computer, the way it does the training is it draws samples from the conditional probability distribution by assuming that these neurons are behaving independently. They don't have any interaction or interdependency. But when we're using the quantum annealer, we can actually draw samples from the original probability distribution. Um, so after we have trained the restricted Boltzmann machine, so what we do is, because as you can see that our approach is basically use the restricted Boltzmann machine to generate an image. And based on the generated image, we want to understand whether the original image was a real image or a false image injected by an attacker. So to be able to do that, what we do is we take an image and we fill in all these labeling pixels with just random 0 and 1. So we randomly fill them in with 0 and 1, and then we feed that image to the restricted Boltzmann machine. And because the restricted Boltzmann machine have been trained on real CAN images and false CAN images, it is able to reconstruct the image. And while reconstructing, we only focus on the labeling bits, because the other features, those are coming from the CAN image or the CAN messages itself. We don't need to reconstruct them. So we train the restricted Boltzmann machine particularly focusing on reconstructing the labeling bits, because that's what we care about for image classification. So after reconstructing those bits, we simply count down like how many pixels among those 16 pixels are denoting that this is a regular CAN image versus how many pixels are denoting that this is a attack CAN image. And the higher the number, the decision goes in that way. So if most of the pixels are telling me that this is a real CAN image, then we think that, okay, this is a real CAN image. Otherwise, we know that this is an attacker generated image. So what we did is we tested this approach on three different data sets. The data sets are coming from Korean hacking research lab, HCRL, I think Hacking and Countermeasure Research Lab is most of you probably know about it. So the from the HCRL database, we got these three different data sets that are associated with different nodes of the controller area network, and we tested this approach. We compared our quantum approach with a fully classical approach. So in the fully classical approach, we are not using the quantum computers at all. The restricted Boltzmann machine is being trained using the contrastive divergence approach. And in the quantum restricted Boltzmann machine, we are using the quantum annular. And for this project, we utilized actually the real quantum machine, the D-Wave Advantage 4.1. We utilized that machine to train our restricted Boltzmann machine. So the quantum RBM here is trained on a quantum machine, and the classical one is a classical machine. And if we look at the results carefully, we see that there is an improvement in the accuracy, which is not very significant, I would say. So you see that for the second data set, we had an accuracy of 95% with classical, but with quantum, we were able to achieve a little bit higher, about 97% accuracy. But what was more interesting is to look at the recall, because when we are dealing with intrusion detection systems, our one of the most important thing is to look at the recall, because we don't need to miss or mislabel any attack images. Every time there is an attack or attack from a cyber attacker, we need to identify that this is a message coming from an attacker, right? So we care more about having more true positives, and having as less as we can, as less mm, as less false negatives as we can, right? So if we compare these two approaches, we see that with the quantum restricted Boltzmann machine, we were actually able to reduce the false negatives, and essentially we increased the true positives. So in this here, we have 32 true positives. While using the quantum, it increased to 36. The last one, we increased from 32 to 35. So that tells us that the quantum restricted Boltzmann machine was able to train better, because it was able to capture the interrelationship between different nodes in the restricted Boltzmann machine. So to conclude this study, so first of all, we leveraged the generative ability of a generative neural network for image classification. Uh, so it's by using the labels embedded on the image itself. So normal image classification, we typically have an image and we have an associated label. We tell the neural network that this is the image and this is the associated label. And over time, it is trained on to understand that what type of image belongs to which class. Uh, as opposed to in this approach, we are actually completely using the generative ability. That's why we embedded the label directly inside the image to be able to just reconstruct the image using the generative neural network, that is the restricted Boltzmann machine in this case. And then just looking at the labeling bits, we instantly know whether it is a false message or a real message. Uh, and the performance improvement in this case can be attributed to quantum tunneling, but most likely it is due to the sampling from the original distribution based on the quantum annealing approach. Uh, the potential of the classical only implementation of RBM. So what the last point is about, it is although we are using the quantum annealer for training the restricted Boltzmann machine, when we are actually using the models, we don't need to use a quantum machine. We can just convert the weights into classical binary bits, and then we can utilize a classical computer, maybe an onboard classical computer in the vehicle to run the model. So the the benefit of using the quantum annealer is only in the training phase. We don't need it after we have trained the model. The second project that I'm going to talk about, it's about the autonomous perception, how we can protect the autonomous perception from different type of cyber attacks. In particular, we are interested in deepfake technology. So first of all, we were looking at how we can use the deepfake technology to create an attack for autonomous vehicle, autonomous perception system, uh, and whether we are able to identify those attacks using a hybrid quantum classical approach.
So, Dr. Salek, I have one comment. because
Yep.
you have two more projects to discuss and there are a lot of questions and answers. So I
Hmm.
have a suggestion. So um, you can just, we have about 10 to 12 minutes. So do you want to, like, there are a lot of questions in the chat box. So
Hmm.
we can do, this is the part one. So the PQC and deepfake, you can do another presentation on another day, sometime later as
Hmm.
part two. Uh, what
Yep.
do you think? Like, so.
Yeah, that is completely fine with me, Dr. Chaudhary.
So,
So,
Megha, so I think that because yeah, I see a lot of questions, so it might be worthwhile to discuss, and we'll have
mhm.
a part two of your presentation sometime later.
Sure, sure. I'm completely fine with that, Dr. Chaudhary.
So, I think let's do that. So you are going to present on the post-quantum cryptography, the third project. So I think that
Hmm.
itself is very important, and also this project too, deepfake, which is
Hmm.
very common attack,
Hmm.
not only on transportation system, but also like an image processing and other video-based systems. I think it would be worthwhile to discuss those two projects in a separate event. So,
Sure.
Megha, if you could like read the comments and we can just discuss the questions and answers.
Okay, so thank you so much, Dr. Salek, for the webinar. So we have a couple of questions from, let's see who, Minaj Ahmed. So Dr. Salek, so we have multiple questions. So do you want to read out the question and then answer?
Uh, Actually, I can read it out myself. Yeah, yeah. I can read it out, Megha. So, okay. So the first question from Minhas, you mentioned that cyber attack has increased, seen 409% increase. Do you think there is any fundamental shift in technology that is motivating this high rate of attacks, or this is just a natural progression and has been increasing historically? Uh, yeah. So I would say there's not one particular technology that we can attribute to for this particular rise in attacks. It's a lot of things, right? So the most commonly the two things that we can think of is the increased connectivity and the automation. So everything is now interconnected. And not only that, we are using many autonomous systems in different cases, not only in transportation, in healthcare, in telecommunication. They're using a lot of autonomous systems to drive the operations, right? So I think it's probably not only one particular technology, but the adoption or the wide adoption of technology and wide adoption of connectivity that is probably causing this major shift in cyber attacks. And I don't think that it's going to go down because we are right now the technological revolution that we are going through. Uh, we do not expect it to go down. That means we do not expect to see a decline in cyber attacks. So the attackers will always have their motivations. So whether it is money, whether it is maybe creating an impact at a national level or hampering the lives of people within a nation, but whatever it is, the attackers will always have their motivation. And with this increment, with these new technologies, we are enabling not only the people who are trying to defend, but also we are enabling the attackers to come up with new attacks. So I see that not only the cyber attacks are rising, but also the defensive strategy for those or the resiliency strategies that can overcome those issues, those are also increasing. So I see that these two things are in hand. So both the attacker side and the defender side.
So I'll make just one. I'll agree with Dr. Salek. Two major components are increasing those attacks. One is open system, and the second is connected system. So these are two primary culprits, and systems will become more open and more connected. So you can expect the attacks to increase exponentially in the future.
Mhm. Thank you, Dr. Okay, so the second question I see from Minhas is it possible to gain wireless access to Canvas by busing any physical connection? The physical aspect is analogous to plugging a mouse or a keyboard into a server room. You can do anything if you have physical access, but that doesn't mean server operating systems will add authentication layer between a keyboard and a computer. So how or what can be? That's a very good question, actually. So to be honest, I don't remember I have seen any study that showed how we can access the canvas wirelessly. So I'm not but yeah, I have seen people talking that this is one of the possibilities. So one possibility is um, you get into the system through some infotainment system, maybe your radio or the other infotainment systems that you have within your car, but directly utilizing the wireless communication to connect into the CAN network. I have not seen um, them doing it directly, but I have seen papers mentioning that it is one of the possibilities to connect to the CAN network. Uh, okay, so the third question I see about the tire pressure change example you gave, the decrease in the pressure can also mean an air leakage in the tire. Yeah, of course. And the rate of change can wildly vary depending on the size of the leakage. So coming from that, how would you classify a change as an attack if the change has a very real physical meaning that can actually happen in a real world? Yeah, that's very true. So that is definitely true. So uh, there are different type of attacks in the CAN network. So we can, one example that I gave is just replaying the same messages again, so that there's no way of knowing it is coming from a real source or an attacker. Another approach is you can look at the previous in the previous timestamps how the sensors or nodes are performing, and you can shift those uh, to kind of in a time series, so you can predict like, okay, in the last 5 seconds it has performed like that, maybe in the next 2 seconds the status will be like this, and based on those predicted status, we can actually inject CAN messages into the CAN network that would be more realistic. So yes, you are right. So it is difficult to detect those kind of attacks, but I see that for every attack type that we have seen so far, there is a counter strategy that we can develop. But the challenge is how we can have a more an approach that is more integral of all these different type of attacks. So attacks can be based on like a denial of service attack. It can be like a replay attack or an amplitude shift attack. But no matter what type of attack we are having, the challenge is we need to have an intrusion detection system that can deal with a lot of this type of attacks simultaneously. So I think that's actually very important, that to be able to, yeah. So the tire pressure can definitely change because of many reasons, but just by detecting the anomalies, we may not be able to detect that there is an intrusion, but we can look at it from multiple perspectives: the message itself, the previous messages, the time series, how it is going from one state to another over time. So by accumulating all those information together, I think it is possible to detect different type of attacks. In your implementation, did you guys use a card that uses old CAN standard or newer CANFD version? CANFD does have encryptions, if I recall correctly. Yes, CANFD has some encryptions, that's right. I think the CAN message that we used, it did not have any encryption. It is based on a Kia Soul vehicle and on the older models. I'm not exactly sure which year it is, but the data set, we did not collect the CAN data directly from the vehicle. The data were already collected. The false messages were already injected. So we used the data set directly from the HCRL website. And I'm pretty sure it did not have any sort of encryption. So that means it is the old CAN standard. For the next question I see is the purpose of constructing image from a CAN packet stream to be able to apply convolutional neural network based techniques. If so, we know that CNN assumes some special relationship with surrounding pixels when it creates feature maps. It uh, guaranteed to have any sort of special relationship of different fields of in CAN packets. Okay, okay. So I guess what you're talking about is if we can capture those relationship, the spatial relationship among different nodes, um, by using the convolutional neural network approach. Definitely, we can use the convolutional neural network approach. We might have to then think about, I mean, the way we have constructed the image, that is very much related to the approach that we have taken for the intrusion detection, because it helps that particular way of intrusion detection. If we want to use convolutional neural network, it is definitely possible. There is another paper from our previous group members, Dr. Mahfuzul Islam. So he actually utilized convolutional neural network to capture the spatial relationship instead of actually
Yes.
embedding the labels on top of the image itself. So yeah, it is definitely possible to do that. From the confusion matrix, we can see that the true positive and the false positive less than 100 samples. Is it safe to test on such small sample set, or it is pretty standard for the field? Well, we can consider the reason so that is why we actually utilize multiple data sets. So we didn't want to conclude from just one data set. We wanted to look at multiple nodes, multiple data sets to see that if we have similar results. So definitely, if we can use a data set that has more data from different CAN nodes and a lot of data from every CAN node, that would be a better evaluation of the approach or any approach for regarding to intrusion detection system. Okay, one question I see from Abiyad. Why are the last two columns used to encode the label in the encoded CAN image? Why not only the last column? Could we consider only the pixels? Could we consider only the pixels of the last column and color them yellow for it? Yeah, definitely we can do that. So it actually came from, came from an attack, like a trial and error approach. So we started with just one pixel. So we dedicated one pixel for the label, and then we started increasing the number of pixels to see like at what level we are able to accurately reconstruct the image. Because when we are reconstructing the image, if we use a very limited number of pixels within the image, a lot of times we might see that the generative neural network is reconstructing them in a way that it is not indicating the right result, the correct result, right? And that is why we have included like multiple pixels. But definitely we can shift those columns to either left or right. I don't think that would have much effect. So even if we use the left two columns, it's very much the same thing, because once we convert those information into the restricted baseband machine's visible layer, each pixel is connected with a neuron. So in any way we can allocate them, we are still considering each of those pixels separately. As opposed to when you are using a convolutional neural network, you have a kernel that is actually moving through the image, right? And then it is the reason to do that is to understand like how the image is transitioning spatially. But when we are using each neuron for each dedicated to each pixel, that spatial relationship is not captured anymore in restricted Boltzmann machine. So it doesn't matter for restricted Boltzmann machine where we are placing those pixels, but what matters is how many pixels we are dedicating for the labels. So that affects actually the performance of the reconstruction. Okay. I see one question from Joel. What is the baseline for classifying benign and malicious node messages? How can we quantify whether a particular message is malicious? So the baseline that we used is a completely classical only approach as compared to the quantum approach that we took. It is a hybrid quantum classical approach. So we could have compared with other convolutional neural network, but that was not the objective of this particular project. The objective was that instead of having multiple stages of defense, we just want to use one very lightweight generative neural network. And that particular neural network will serve the entire purpose of reconstruction and classification at the same time. So we didn't want to include one network for generation and then one network for classification. We just wanted to have just one network that will be able to reconstruct, and we will be able to classify using that reconstructed image. So the motivation was to make it lightweight.
I just want to add one thing, Dr. Saleh. So the audience, I think Minhas mentioned about the wireless. Can you enter wirelessly to the canvas? You can definitely do that. There's sometimes wireless protocol vulnerability that you can utilize. Keyless entry can also let you into the canvas, Bluetooth, and also Wi-Fi hacking inside the vehicle. You can enter the canvas network,
Mhm. Yeah.
as you mentioned.
Thank you, Dr. Chaudhary. Uh, okay. I see that Imtiaz mentioned this Jeep attack in 2016 was done wirelessly. Thank you, Imtiaz. That's a very good information. So I will look into that. Um, and then, okay, is there any other question I'm missing? Okay, I see. Okay, yeah, I think I covered unless
So Dr. Imtiaz mentioned something about latency. If you see the canvas latency will be impacted. Latency, one of the major factors. You see Imtiaz's
Oh,
comment.
yes. Now I see, sir. Thank you. So the question I have is how the performance can message latency will be impacted in your opinion. So latency is one of the major factor why many of the manufacturers are reluctant to implement encryption in Canvas. Yeah, that is the primary reason that the encryption is not part of the original CAN protocol. Um, uh, so I'm not sure I understood the question. So is your question that if we include encryption, whether we still have the leg room to implement an intrusion detection system?
Uh, no, Dr. Sarek. So my question was actually, if we implement the attack detection technique like the quantum classical hybrid model, then how the latency will be impacted in your
Okay. So you're saying that having the intrusion detection system in place, would that affect the latency, right?
yes.
That's a very good question. Actually, we have not evaluated how much it would impact the latency, but this type of for another project we evaluated in terms of like the onboard computational performance. So the models that we typically are developing using high performance computers, right? So maybe we are using GPU, we are using cluster computing to develop models, but are those really implementable in the onboard computer of an autonomous vehicle? So I have looked into the most recent like the onboard computers that NVIDIA are developing, like the Orin or the
Yes,
Jetson Nano, and those actually have multiple teraflops of information that they can process every second.
yes, it's
So
very
that
powerful.
that is extremely powerful. That is actually on par with a lot of high performance computers, and those are onboard computers on a very production level or the commercial level they're developing. So I don't think latency is much of an issue for this type of intrusion detection system. Mostly, in most cases, the intrusion detection system people develop those are like anomaly detections and those are most of the times are quite lightweight. So yeah, I don't think the latency would be a major issue for CAN intrusion detection system.
Thank you, Dr.
I think that, thank you, Dr. Salek. Wonderful presentation, very clear, and you described in
Yeah.
detail. So you understand it very well, and you just brought in some very new topic to cybersecurity of autonomous vehicles with this Bozeman machine and restricted Bozeman machine. So I thank you for bringing this new technologies to our center. So thank you.
Thank
And
you.
as Megha mentioned, the recording will be available on our YouTube channel. And if you have further questions for Dr. Salek, please email Megha or Dr. Salek. So they will answer you on the right time.
Yeah, yes. And also one more thing before everyone signs off. So we'll have part 2 of this webinar on post-quantum cryptography. So once we have a date and time set, we'll keep everyone posted and we'll announce it. And for now, thank you again all for participating, and we look forward to seeing you at our next webinar. Have a great day and a great week.
Thank you all. Thank you very much.